title slide. So let's move quite quickly through this material. Of course, as usual, you will be provided with a PDF copy of all of these slides. That will be downloadable shortly after the event has finished. So, as I said, this is the third in this series of webinars on topics of geotechnical engineering. And today I want to talk about this really important principle of effective stress, and then also measuring soil strength using the triaxial test. And in fact, in this case, the target will be measuring the effective stress parameters, C' and phi', which we need to know in a lot of our designs, especially when we're using soils as fills. I shall look briefly at undrained shear strength, but in fact, that will come up in a later webinar. The webinar after this one is going to be looking at the use of clay fills in soil structures in general, but in particular in reinforced soil structures. In fact, here is the current plan for these this webinar series. We're now in the April one, and you can see the May title there also. The ones beyond that may change slightly, and there may be some small additions as we go along. But it tends to, we'll see that as we go along what content appears to be most useful for people. If you want to watch the earlier webinars, then there are links available from PT Multibangon to help you view those if you wish. So a few images, a couple of important people, we'll come back to them in a minute. An early piece of equipment, setting up a triaxial test. More like the modern equipment we tend to see today, and all of the controls that go with it. So we'll learn more about that towards the end, the actual testing. But first of all, we want to look at the principle of effective stress. So that's the first part of the webinar. And then in the second part, we'll look at the triaxial test itself and cover certain points. It's not going to be a total explanation of every aspect of the test. It's the main points. And if you really want to know more details, you need to find manuals and standards that give you the full information. As we go along, these little blue boxes will pop up quite regularly, which provide some additional information, and they also pose a few questions. Now, the material today is aimed at civil engineers, particularly those who have involvement in ground engineering. More experienced geotechnical engineers might find this useful, but the main target, of course, from the point of view of what I work in, is reinforced soil applications, but it's appropriate to any kind of soil structure. So I hope a wide range of people might find this useful. I think in particular, and I showed a similar slide in the last webinar, when engineers receive geotechnical reports, then they often see tables of data like this, where we have all kinds of measured parameters. And in this particular case, the right-hand columns mention triaxial test results, C' and phi'. And I suppose the aim of today really is to look at that data and decide, should we make some investigation to be quite sure whether or not this data is reliable, is as it should be? And I think you're going to see later on the answer is yes. We need to understand where this data comes from before we put it into our design calculations. And let's jump straight in. The principle of effective stress. And we've got a little soil element there and a well-known equation. And the elements are like this. So we have a total stress which is applied to this element, sigma, we normally call it. And then inside the element, we have water in the pore spaces. And the pressure in the water, we normally give the symbol U. So that's the pressure in the pore spaces in the water. In this particular case, we're assuming that we have no air in there. It's only water in the pore spaces. And then the difference between the two of them is the effective stress. And what is the effective stress? Well, the effective stress essentially is the load carried through the contact points between the soil particles coming out at the other end. That is the effective stress. Now, there are two important principles that follow on from this. And the first one is that shear strength in the soil for example, on a shear plane there, where you see the green arrows appearing, that depends on the effective stress. And also, if we add some measurement of volume change, which you can see there over on the top right, then the volume change also depends on the change in effective stress. And this, in a nutshell, are the important aspects of this discussion. But I really want to put some more details to this and see how it all works. So we're going to come back to this little soil element shortly, but some other things first of all. Some of those important people, Carl Tensar, the idea of the principle of effective stress is attributed to Tensar. And in his time, it was well established for permeable soils like sands and gravels, but the situation with clays and low permeability soils was not quite so clear. And in fact, at that stage, it was rather more of an empirical solution. Then along comes another gentleman. This is Professor Bishop. And in the 1940s, Bishop started work to improve this situation, in particular with regards to effective stress in fine soils. There's a very nice picture of him. And here's a rather nice picture. In fact, it's Bishop's first triaxial apparatus. And the gentleman standing behind it, I'm sure many of you will recognize him, it's Laurie Wesley. I'll come back to him again in a second. And this piece of equipment was built in around about 1944. And if we look at this little label that's attached to it, there's some information about it here. I'm not going to read through this. It'll be in the slides when you get them. But what's rather important is at this stage in his career, Bishop was actually working in industry. He was working for what was then called the Metropolitan Water Board, designing embankments that retain water supply all around the west side of London. Anybody who drives around there will see these things. And Bishop actually moved to Imperial College in 1946. So he had this early experience working outside the academic world, but after 1946, he remained an academic for the rest of his career. But I just want to make a bit of a personal recollection of Bishop. And I have this notice, which I've kept. And it's a notice of a BGS meeting in 1974. And I've always wondered slightly why I kept it, because I haven't got any others. And it's an informal discussion about a very hot topic at that stage, which was the stability of cuttings in over-consolidated clays. And as a young graduate engineer, I went up to London to the Institution of Civil Engineers to listen to this. And there was a very heated discussion going on with many of what you might call the big names, having a wee bit of an argument about this topic. But then what was quite interesting is that when we got towards the end, the room went a bit quiet, and a gentleman was walking slowly to the lectern, and as this happened, I could hear whispers around me saying, "Oh, it's Bishop." And sure enough, this man stood there, a rather pale-looking man in a black suit, with his head mainly downwards, looking at the lectern, and he made a few comments about the discussion. It brought the whole meeting to a close. Everybody got up and quietly walked out. And I have to say, it left such a big impression on me. I felt, we all knew about the soil mechanics course at Imperial College. I felt this is something one should try and do. And luckily, 2 years later, just over 2 years later, I was at Imperial College and I was listening to Bishop's lectures, which were on a Thursday and Friday afternoon. And here you can see in my handwritten notes, you just about read it, the principle of effective stress. And this was very much awaited, and I'd have to say it was a wonderful experience listening to Bishop delivering this kind of information. Now, if you want to know more about it, luckily we have some help on this. Bishop had become somewhat forgotten, but luckily, again, our friend Laurie Wesley was persuaded to write a biography about Bishop, which is the book, the reddish-colored book on the left there, The Bishop Method. And I would thoroughly recommend that people try and get hold of this book. It's quite short, but it tells you about his life, but also about his work and the build-up of the work that he did at Imperial College. It's a really interesting book, written by Laurie Wesley. And at the same time, Laurie also managed to get agreement to publish a series of Bishop's more important papers, which are in the yellow book. And that one you can also buy from the same publisher. I've given the references at the end of this if anyone's interested to know more. And here are two of the important papers. On the left, you have the principle of effective stress. Clearly, this really is the topic of today. And then on the right, you have a book about the relevance of triaxial testing to stability problems. And in fact, this one is referred to as the Boulder, Colorado paper, and many people would probably recommend or rate this as one of the most important papers written in soil mechanics. Difficult to get hold of, but you can get it if you buy that book of papers. But it really does lay down the foundation to how you use triaxial testing when we look at the stability of structures in various situations. It's actually quite interesting that Bishop only published 68 papers. By modern day standards of professors and academics, that's quite a small number. But of course, what was important was the content and quality of the papers. I thoroughly recommend, if you haven't read any of Bishop's papers, try and get hold of them, because they're very readable and they give you this kind of feeling of this early development of soil mechanics, which was so important to what we do today. A couple of books about triaxial testing. They're both rather old. I don't know if there are any more modern ones, but the blue one on the left is volume 3 of the series of books by Ken Head. And this one is about effective stress testing. And the other book, the green colored one, is one of my prized possessions on my bookshelf. It's the only book that Bishop ever wrote together with Henkel. And although it sounds like it's about the triaxial test, it is, but it's an awful lot more. It contains an awful lot of Bishop's soil mechanics and everything that came with it. And I've referred to that book in producing this presentation today. So, summary and content. Well, the introduction, I finished that. We've done that already. We've had the introduction to this webinar. A quick thing about effective stress rules. Okay. Then we're going to talk a bit about embankment stability. And then we're going to look at stresses. We're going to go back to our little soil element and look at the stresses and behavior of the soil element. And then after that, the triaxial test procedure. I'm not going to spend a lot of time on that, but we look at the basics. Then we look at some case studies, some examples of results from both CU and CD triaxial testing. We'll learn more about what those things mean shortly. And then at the end of this, I'm going to attempt to answer 2 questions which I posed in the first webinar, and I hopefully explain how I see the 2 particular situations I talked about then. As you know, there will be a quiz at the end of the webinar, which is going to be related to some of the material presented, and there will be prizes for the winners. Just a couple of points is that this webinar is really only looking at the case when soil is fully saturated. In other words, typically foundation soils, especially soft soils below the water table. And in the next webinar, we're going to look at the use of clay fills, which is the case when these soils become partially saturated or unsaturated. So that is how I've structured those 2 webinars. So here we are, effective stress rules. Okay, so here's a fairly unimpressive failure of a low height embankment. It's actually in Malaysia, not far from the island of Penang. And you can see this embankment maybe about 3 meters high. A very, very classic looking failure into a drainage channel on the right. And if we look over on that side, you can see how the material is heaved up at the toe of that failure. So if we think about a little bit of a cross section, there was our embankment, high water table, and we've had a failure something like this. And of course, the point is, and the question is, well, what about the effective stress in the foundation soils? What was it? Because we've already seen that that's going to control the shear strength. So we need to understand about that. And this is one of these really important aspects of soil mechanics, being aware of the situation with effective stress in a situation like this. So that's what we're going to do. We're going to look what happens when we build an embankment over this kind of foundation. And we're going to do it starting from the beginning when there's no embankment. So here we have a simple situation of the soil mass and a water table. And then we have the little blue soil element we're thinking about. We have a height above it of soil and a height to the water table and some parameters. And we can calculate the stresses. So just the vertical stresses at the moment. So we can calculate the total stress is very simple, just the height times the unit weight of the soil. Water pressure equally easy, just the height to the water times the unit weight of water. And then for the effective stress, we simply subtract one from the other. And there we have this important parameter. We then come along and build an embankment. And on purpose, I've removed the water table. And to begin with, we're going to look at the case where we have a high permeability soil. Now, in fact, in all cases, for all soils, there will be an increase in water pressure, even if that is a gravel. But at the normal rate of construction, in the highly permeable soils, those excess pore pressures, as we call them, they will dissipate as fast as you build. So you will actually always just see the hydrostatic pore pressure line, so I've put it back in the diagram now. This means that we can now calculate the pore pressure. Just to remind you, this is when we have a high permeability sand or gravel in the foundation soil. So if we want to look at stability of this situation, we're going to do some kind of circular analysis. There's our slip circle with its radius, and it's going to move as shown by the red arrow. And what we can then do is to go in there, and at various points along that surface, we can calculate the shear resistance. And then what we need to do is to equate the driving moment to the total resistance times the radius and check the stability of that particular surface. So to do that, we're going to make use of what we call the Moore-Coulomb relationship, which gives us a relationship that says the shear strength equals C dashed plus the effective stress times tan phi dashed. Just to remind you, we're looking at a drained analysis because this is what we're going to do with highly permeable soils. So we go back to our cross section, and this means that wherever we see the S, we can now calculate the sigma dash. And because we know sigma dash, we can put that into the Moore-Coulomb equation, and we can find those resistances. Just to remind you, we're calling this the drained analysis. So we can find out sigma E, for example, by the method of slices or finite elements. And we need to know U, but we're now assuming that we have hydrostatic conditions, so we know that as well. So we know our effective stress. So the whole system works. Now, if we then change to low permeability, fine soils, like, for example, clays or clay silts, then when we build our embankment, there will be an increase or a change in pore pressure, and it'll take a very long time for it to dissipate. Therefore, we need to use a different approach in classical soil mechanics. So we need to use a technique where rather than trying to assess the pore pressure, we're going to go inside the soil and measure S directly. So here is our embankment again. So we build the embankment over a low permeability, say, silty clay. And U is a big question mark. We don't know what it is. So what we're going to do in that case is to actually take out samples and measure their shear resistance. And of course, this is what we call undrained shear strength. And then we're going to use this very simple definition to say that S equals the undrained shear strength. And the nice thing about that is that we no longer need to know sigma E or U. But the problem is, we're going to have to measure the undrained shear strength in every single situation on every site. We cannot easily guess it or estimate it. Unless we have a lot of knowledge about a site, we need to go and measure it. So that's what we do. We measure SU, and we can then complete our analysis and look at the stability of that particular embankment. And this would be what we call an undrained analysis, because we're using, it's a short-term analysis, and we're using the undrained shear strength to do it. Now, I mentioned earlier on that we're going to look at methods of measuring undrained shear strength in a later webinar, so we will do that later on. But also we can look at long-term conditions. So if we wait a very long time for all the excess pore pressures to dissipate, then we can go back to assuming the hydrostatic condition as we had for the permeable soils, and we can do our analysis again using the Moore-Coulomb equation and taking into account the pore water pressure. So the drain analysis is possible, but it's going to be in the long term generally for low permeability soils. But you might say, well, I'd like to try and analyze the short-term condition in the clay foundation using C' and Phi'. So is there a way to assess the increase in pore pressure? And the answer is yes. We can do this using what are called Skempton's pore pressure parameters A and B. And I would just like to mention them because they're going to come up again at a number of places in the remaining part of this webinar. So let's see what we mean by this. So let's go back to the beginning again. Here we got our initial stresses, but in this case, I'm going to calculate both the vertical stresses and the horizontal ones. So the vertical stress, we're going to call it sigma 1, and we can calculate that much as we did before. And we get it there, and the vertical effective stress, we can just find that by subtracting the pore pressure as we did. And then to get the horizontal stress, we just take the vertical effective stress, we multiply it by K0, that's the coefficient of earth pressure at rest, and we add on the water pressure again, and we get sigma 3. So we've now got the complete system of total stresses applied to the element. We now come along and build our embankment again. And again, we're not quite sure what the water pressure is, so I've removed the hydrostatic line. But we can calculate the additional stresses, both the principal and the major and the minor principal stress directions, sigma 1 and sigma 3. We can calculate the extras, the delta sigmas. And then we have these equations where we have Skempton's parameters A and B, which allow us to make an assessment of the increase in pore water pressure. And you can see the equations there. And essentially, the second version of it divides it into two bits. We have B times the increase in all-round stress, sigma 3, and A bar times the what's called the deviator stress. If you like, it's the additional stress applied in the principal stress direction. And from that, we can then calculate delta U and put that into our system, our equation there. And that allows us then to use the effective stress approach to look at the stability of that embankment by calculating the increase in pore pressure. Now, the values of these A and B parameters, well, for saturated soils, B is essentially 1. So that's fairly simple. But A is a bit more difficult because A depends on quite a few things, in particular on the overconsolidation ratio. And for very, very soft soils, A can be as high as 1. But for stiff soils, A could be as low as 0 or even negative. And we'll see later on exactly what that means in terms of behavior. But that's the typical range of values of this A parameter. Now, for those of you who like to use Plaxis or other FEA programs, this is essentially the same as what's called the undrained A procedure. And if you're going to use that in Plaxis, please read very carefully section 2.5 of the Material Models Manual of Plaxis, which gives some fairly severe warnings about the potentials for inaccuracy in doing this and making sure that you check what you're finding against measured undrained shear strength. That's a whole different story, not part of this webinar today, but I thought I'd just make a point about that at this stage. We'll talk about this A parameter a little bit later on during the webinar, and what it means. So what I want to do now is to isolate our little element. It's down there at the bottom of the screen, and I want to look at it in slightly more detail, and I'm going to make it look bigger. So here we are, expand it up a bit. And I'm now going to put in there the soil particles. So it's rather like the picture I had earlier on when we talked about that principle of effective stress. Of course, the brown elements in there, they represent soil particles, and the white is currently void space. And we're assuming it's a dry soil at the moment. And the way we're going to do this little exercise is that this box has got rigid sides, but the horizontal, the sides on the edges, so the box sides on the edges, the horizontal ones, they are held there by horizontal stress. But the top and bottom is like a piston. So the top of the box can move up and down like a piston. And what we need to remember at this stage, two important things, is that in soil mechanics, we're going to assume that the soil particles themselves are incompressible. But the skeleton of soil particles, that's to say the assembly of them that you see there, is compressible. And then at the top there, I'm going to put our important little equation about effective stress. So as I said, this is currently a dry soil. So what we're going to do is apply sigma on the top. And that's going to be transmitted down through the particle contacts until it comes out at the bottom. And there we, of course, also have sigma. And that's going to create a horizontal force that has to be resisted on the edges by K sigma. And you'll see I've now allowed it to deform. So there is volume change due to that, due to the compressibility of the soil skeleton. And the compressibility is given there as delta V over sigma. As I said, that's the compressibility of the soil skeleton. So that means the assembly of particles, not the particles themselves. Now, an important thing here is that the sum of all those forces passing through the elements over unit area is the effective stress. And therefore, the compressibility is actually delta V over the effective stress, assuming that we have a unit volume of material. Now, having got that situation with the stress applied, let's look at this shear surface just through there, the green line, and what therefore is the resistance on that surface at the moment to shear? And the answer is, it's going to be the effective stress times the friction between the soil grains. Of course, we put that into the more Coulomb formula, but in a more fundamental way, that's what it is. Okay, so I hope you got the picture about this little box and how it works, but what I want to do now is, rather than have soil in there, soil particles, I'm going to put it full of water. And it's only water, and again, from the point of view of soil mechanics, we can assume that water is incompressible. There's no air free, there's no free air in it. But we're going to put here a little meter to measure the water pressure. So we apply sigma, we have to restrain the sides, and then we are going to measure also the volume change. So you've got the picture. So there are three questions here. What is U, what is delta V, and what is K? Now, if I was going through this rather more slowly, as it were maybe in a university lecture, I have a little Q&A piece of paper, which in fact we did arrange for you to download if you wish. And the idea is that you should try and answer these questions and fill them in on that piece of paper. So if anybody has managed to download the little question sheet, then this particular part of this exercise is called Water 1. And the idea is you give me the answers to what is U, delta V, and K at the moment when we apply the stress. Now, I've got to be quite quick today because of this being a webinar and I have a limitation on time. So I'm going to be fairly quick with this, but have a go yourself as we go along, because I'll give you the answers almost straight away. But if later on you want to go back yourself and make sure you can follow this, then of course you're welcome to do so. Anyhow, the answers are that the pore pressure is equal to sigma, the volume change is 0 because water is incompressible, and K equals 1 because in a hydrostatic condition, the pressure in the water is the same in all directions. So there we are. That's the answers to Water 1. Right, so what's the next thing we're going to do? Oh, that's just a reminder that because its water is incompressible, delta V over sigma currently is 0. So at the moment, there's no drainage. There's no way to let the water out. So what I'm going to do now, I'm going to complete my little my little model by adding a valve on the side, or a tap. So currently the tap is closed and there is no drainage. I then turn the tap so that the water starts to dribble out. And having done that, I'm going to ask the same questions again. While this is happening, what is U, what is delta V, and what is K? And this is question called water 2. And again, I'll have to be quite quick answering these. I can't give you too long to do it, but the answers are going to be, that this is with drainage. Well, U will still be sigma. Delta V, of course, is getting bigger and bigger. That's just increasing all the time. And K is going to be 1 still. That's with drainage. So that would be the answer to water 2. Of course, if you leave the tap open continuously, eventually all the water will drain out. I'm sorry, I put my tap slightly high up on the box, but assuming it was right down the bottom, all the water would have run out. But here's another important question. While the water was running out, does the rate of flow remain constant or does it change? This is kind of an important question, and that's part of the question water number 2. Now, we're going to put everything together. So we're going to put our water and our soil particles inside the box, and we're going to do really the same thing again. So currently there are no stresses, and at the moment what we want to do is to look at our shear surface that's in there, same place, and ask the question, and this is question number soil and water 1, what is the shear resistance on that surface? We assume in this case that this is a tiny particle, and the weight of the soil grains is so small that you don't even notice it. So we're assuming that essentially there is no weight from the grains themselves, the soil grains. And of course, if that's the case, then the shear resistance must be 0, and that's because the effective stress is 0. Now, what I'm going to do now, I've got my tap there, and I'm going to leave the tap closed, and I'm going to apply sigma. There we go. And having done that, tap closed, the question is what happens? Questions are, just put down, we've got to put our horizontal stress there. Same questions again. What is U? What's the change in volume, delta V? And what is K? And this is where it's beginning to get really important with regards to understanding what's happening inside soil in this situation. So let's just draw in our effective stresses. We got the forces coming down through the soil grains, as we had before. Sorry, whoops. Let's go back. Those soils. And therefore, the other question is, what is the effective stress at the moment in this situation? And these are the answers. That the pore pressure U is equal to sigma, delta V is 0, and K is 1. And the effective stress is 0. Now, this is a really important part of this whole discussion. Why is the effective stress 0? Well, the answer is like this, that we have a compressible soil skeleton, and we have incompressible soil particles and incompressible water. So when you load that system with no drainage, the volume can't change, which means you've got, if you like, a very soft spring represented by the soil skeleton and an almost rigid one represented by the combination of water and soil particles. So all the sigma, all the stress is carried by the water. And this is kind of really important place. And that's what that little blue message is telling you there. So the important point is the soil skeleton is compressible, but the rest of the system is incompressible. In fact, this is the explanation of Skempton's B parameter being 1 for saturated soils. You apply a stress, which is an all-round stress, and it all goes into the water pressure, which means that the Skempton's B parameter is 1 for saturated soils. Let's look at our possible shear surface. There it is. So we put in our little arrows. So currently, what is the shear resistance on that surface? And it must be 0, because all of the stress through the system is being carried by the pore water, and there's nothing going through the soil grains. So think back to the failure of that embankment in Malaysia just now. Maybe that's what was going on, or something very close to it. Right, so we've still got the tap closed at the moment, and we tend to call this situation undrained because there's no water flowing out of the system. So we call it undrained. What we're going to do now is to open the tap, and we're going to let the water flow out until it stops. And once the water has stopped flowing out, then what is U, what's delta V, and what's K, and what's the effective stress? So again, if I had lots of time today, I'd give you a couple of minutes to think about that, but I'm going to have to answer those questions fairly quickly. Just put our effective stresses there. So what you'll see now is that the whole specimen has compressed. So in other words, we now have a compressible system. One interesting question before I get to the answer is, does the rate of flow remain constant? I asked that question earlier on with water only. So as the water drips out, is it always at the same rate, or will it change? I haven't given you an answer to that question. It's something you might like to think about and answer for yourself. Anyhow, this is the process that we call consolidation. And to answer the questions, U becomes 0. It has to, because we've opened our tap to the atmosphere, so that becomes 0. And delta V is therefore the same as in the dry case, because you have a compressibility based on the soil skeleton only, and K becomes K0 again. And the total stress becomes the same as the effective stress. This is all called soil and water number 3. I just meant, yeah, so K0 is this term, the coefficient of earth pressure at rest, something we talked about in the first webinar. Again, if we now look at a possible shear surface, there it is. And we look at the shear resistance there. And what is it? Well, it's now going to be the effective stress sigma dash times the friction between the soil grains. In fact, it's the same as the dry case. So I hope that's been a fairly reasonable explanation as to what's going on inside our soil element. Just one important point to make, and I'll make this point again shortly, is that in geotechnical problems, we can normally calculate or measure total stress fairly easily. And we can often assess pore pressure. But the only way that we get to effective stress is to get the two of them and subtract one from the other. We can never get it directly. This is a rather important point when we're looking at any kind of stability problem. Now, I haven't quite finished with the soil element. I just want to do one more thing. And I want to look, so far because this situation is a saturated soil, then this is what's going to be happening for natural soils below the water table, rather like the embankment we saw earlier on in Malaysia. And as I mentioned already, in the next webinar, we're going to look at soil or clay fills, which are partially or partially saturated or unsaturated. And what we'll do then, we'll continue with our little soil element story and look at the effect of adding air to the pore water, which changes things quite a lot. But that's going to be in the next webinar. But there's one more thing I want to do with the soil element before I leave it behind. I want to look what happens when shearing takes place in undrained conditions after initial consolidation. I'm going to look at two cases, a dense soil and a loose soil. Now, I will go through the dense soil quite slowly because there are some important concepts to think about. And also it's on the question sheet. And for the loose soil, I'm going to do it rather more quickly because it's much the same as dense. It's just kind of the other way around. Let's see what I mean. So here is our soil element again. And you can see I've made it look very dense. Lots of soil particles in there, not much room to move at all. And if you look at the system at the moment, the tap is open. So it's consolidated. And if it's consolidated, U must be 0. And we have the horizontal, you can see the water dripping out. And we've got the horizontal stresses are given by K0 times sigma. And therefore, the sigma equals sigma dash at this stage, because pore pressure is 0. And we're going to, this is on the little question sheet, this is called undrained shear and dense, number 1. So I now close the tap. You can see that? So the situation becomes undrained in our little element. I'm now going to apply the shear stress. So I go inside there somehow, and I apply that shear stress. Now, when I do that, because this is a very dense soil, in order to shear, the soil particles have got to move apart. We call it dilation. They have to move apart. So let's actually show that happening. There you are. The soil particles are trying to move up, but they cannot move. At the moment, it's not possible because there is no way that that can change its volume, because there's no water coming in and out, and all the elements inside there are incompressible. So what happens is that, well, these are the questions. What happens then to the effective stress, and what happens to U, and what is the shear resistance when this happens? Well, the effective stress must increase because we're pushing harder upwards and downwards. Then we must be getting a higher effective stress between the soil particles. And then by the principal effective stress at the top, the equation up there, this means that the pore water pressure must be going negative. It's decreasing, so it's going negative. In fact, it's becoming what we call suction. And in fact, this is the reason why Skempton's A parameter would be low or negative in this kind of soil, a very dense, well-compacted or stiff soil. Skempton's A parameter would be low or negative because we're generating a negative pore pressure when we shear in the undrained condition. So at the moment, the shear resistance equals C dash plus sigma minus the effective stress, which is minus U, times tangent of phi. So that is our current shear resistance. What we're going to do now, as you might guess, is we're going to open the tap. So to do this, we open it, but we need to have a little reservoir of water there, which I've just added to the diagram, so that this means that the water can now come to equilibrium with the atmospheric pressure outside. And we're also going to want to know about the volume change. So questions are, when I open the tap, which way does the water flow? What is U? What is delta V? And what is the shear resistance when it all comes into equilibrium? Well, again, this is the question number 2 under undrained shear and dense. And I'll have to answer the questions fairly quickly myself. Well, of course, water must flow in because the water is in a state of suction. So the water goes into the sample, which means that the volume increases, as you saw just then. And that means that the shear resistance must decrease. So the original shear resistance was C dash plus sigma plus U times tan phi. And then that now becomes C dash plus sigma times tan phi. There is a reduction in shear resistance. And that's a situation that we call softening. That loss of strength due to an inflow of water in this situation is what we call softening. You'll often hear that term used in soil mechanics. So this material is softening, and this is the reason why. Now, if I switch over to undrained shear for loose, then because of time, I'm not going to go through it very slowly this time. It is the same idea as for dense, except now it's the other way around. The only difference now is that when we first of all, we just make our situation undrained, and then we're going to apply our shear stress. And what will tend to happen here, and because of the way I've drawn it, you're going to tend to get more of a collapse. As you start to move those soil particles around, they'll tend to collapse. And what will that'll tend to then result in is a change where we get an increase in the pore pressure and therefore a decrease in the effective stress. So it's the opposite way around to the dense condition. So those are my questions there. What happens to the effective stress? What happens to you? What happens to the shear resistance? Well, the effective stress decreases. And because of that, U increases, and therefore we get a reduction in shear resistance. And in this particular case, Skempton's A parameter would be very high, maybe as high as 1. So now after this has happened, we get a shear resistance like this. And then on opening the tap, the water is, of course, the question is, which way does the water flow now? Well, of course, the water will flow outwards. And then like that. So U becomes 0 when it's finished flowing. Delta V is going to be negative. The volume will decrease. And of course, the shear resistance will increase because of the increase in effective stress. So the shear resistance used to be C dash plus sigma minus U times tan phi. That now becomes C dash plus sigma times tan phi. So we get an increase in strength. So that is the end, I think, of this little description of what happens inside our soil element. Of course, real soils don't have taps, but we can, because of low permeability in clays like in soils like clays and silts, then in the short term, the rate of flow is going to be so slow that it behaves as if it was undrained. And that's why we use this terminology of undrained or drained behavior in the finer, low permeability soils. So I think that's the end of that little discussion on the soil element and what goes on inside it. So we're now going to spend the rest of this looking at the triaxial test. It won't take me quite so long to do that. So here we are. There's a nice little cross-section of a triaxial test cell. This shows the principal elements of the test set up for what we call a total stress test. And these would be the so-called UU triaxial tests. That's to say, unconsolidated, undrained triaxial tests. The main elements are that we have a cell, and inside the cell, there is our soil specimen. And we apply a cell pressure down the bottom there called sigma 3. And having done that, we can then fairly quickly apply what's called the deviator stress on the top, which is therefore sigma 1 minus sigma 3. And we do that until it fails. And from this, we measure the undrained shear strength. The equipment is fairly simple to do this. And in most soil laboratories, the total stress triaxial equipment will be out in what we might call the general laboratory because it's a fairly simple test to do. And we will look at a bit more at this one in a later webinar when we talk about undrained shear strength. But for today, I'm going to leave that behind because I want to concentrate on what we call the effective stress tests. So here we are. So this is now switched over to the requirements of a triaxial setup to measure C dash and phi dash. In other words, the strength in terms of effective stress. There are two kinds of procedure, CD, that's consolidated drained, and CU, which is consolidated undrained. And we'll look at both of them briefly. You'll now see there's a bit more going on because we also have connections to the top and bottom of the sample through the end caps where we have a porous element. And we have additional connections now. We have 3 connections coming out of the bottom of the cell now. And we're going to use these connections either to measure pore pressure or to measure volume change or to apply what's called back pressure. I will mention that again briefly in a second. Now, if you read Bishop's book, you'll find out all about this. But the equipment in those days was very different to what you'll see today in a modern laboratory where we use transducers and all kind of clever devices to control this test. Very different to the days when Bishop was developing these ideas. So here we see a specimen set up to do effective stress testing. That's actually a sample of Singapore marine clay. And having got it on the pedestal there, the next thing we do is to add the membrane and some O-rings. And then we complete the setup. You can see quite clearly there in the picture how you've got the 3 taps. And you can see a bit of a tube coming up. This is going to be stuck on the top one. And so there is, I mean, this is a picture from a catalog. It's from, so you can see there the full setup. Now, the control of this testing is much more complex and elaborate than the undrained test. So normally this kind of testing is carried out in a special effective stress laboratory where we have to carefully control temperature and all sorts of things to make sure these tests are carried out as well as they possibly can be. So the basic procedure, actually, if you remember, or if you attended the webinar about shear box testing, it's really the same. There are 3 main stages to these tests: a saturation stage, then a consolidation stage, and then finally shearing. And the shearing can be done either undrained or drained. So we'll have a few words about each of these. So the saturation stage, this one is really important. We're only going to get good data from this testing if the entire system is saturated, which includes the sample itself. If you've got air inside it, then you're not going to get the right results. So we need to saturate the sample. And if you simply put it in contact with free water, you're not going to get rid of the air. So what we normally do is to use what's called back pressure. And in this case, what we do, we put in a fairly high cell pressure and we put the same pressure into the end caps. So the soil particles don't really see any difference, but the pore water does. And by using a high back pressure, we can essentially dissolve the free air into the water. And so if you ever see a result where it talks about back pressure, that's the reason for it. But when it comes to analyzing the results, you haven't got to worry about it. Now, when it comes to the shearing stage, if we're doing a CD test, that's a consolidated drain test, then the idea here is that the pore pressure is going to be 0. And the only way we can make sure that's the case is to do the test incredibly slowly. So a CD triaxial test is going to take a very long time, especially if you use a larger sample. In the normal small samples, it might take a day or so to shear it. But in larger samples, it can take much longer. When we do this, we're going to use the connections down at the bottom right to measure the volume change and also to check that the water pressure is being maintained at 0. We need to remember, though, that shearing is taking place in the center of the specimen. That's where most of the pore pressure is being created, and it's got to get to the ends. This is particularly important when we look at the CU test. So you might say, well, with shearing, can't we do it very quickly now because we're not worried about dissipation of pore pressure? Well, that's correct. But we are worried that the pore pressure we measure at the ends of the samples should be the same as the pore pressure in the center. Therefore, we still have to do the shearing quite slowly. And again, manuals and procedures will tell you how to calculate these rates of shearing. But again, we cannot test too quickly. Otherwise, we'll measure the wrong water pressure. So in a typical test, we're going to have these results: axial strain, cell pressure, the deviator stress, which is the stress on the end of the sample, the top, and the pore water pressure, which we measure. This is for the CU triaxial test. This is the main one I want to talk about. So we tabulate those results. You can see there, we've got 4 columns results. The strain starting at 0 at the beginning of the test, and that's going up. And then the sigma 3, of course, stays constant because it's a total stress. We got the deviator stress, sigma 1 minus sigma 3, and the pore pressure. And what we could do if we wish, we could plot, say, the deviator stress and the pore pressure against the axial strain, and that particular test would look like that, which is quite an interesting plot. And in fact, if you want to assess stiffness for this particular soil, that would be a good way to do it. But if you want to assess failure, we've got to do this in a different way. So let's see how that works. So what we're going to do now, go back to our table of data there, and we're going to calculate the various principal stresses, sigma 1, sigma 3 dash, and sigma 1 dash. And once you've got those principal stresses plus sigma 3 originally, we can then plot Moore's circles on a diagram like this. So I've done a Moore's circle for each of the stages of the test. The blue circles are total stress, and the red circles are effective stress. So that means that we can assess failure as a line touching the failure circle on the red circles. Now, of course, to do that completely, you'd have to do several more tests at different cell pressures, but let's just assume we've got those and we're just looking at one of them. So that's what the results look like. But if we plot every result like this, it's kind of messy. If you've got many stages, you're going to have so many circles, you can't really see what's going on. So to overcome this problem, what we're going to do is to plot the coordinates of the top of each circle because it's a unique value. So we calculate those like this. So again, in our table, we calculate the coordinates of the top of each circle. I won't read them through them there, but you can see them in those 3 columns on the right. And having done that, we then join those points together. That's the heavy line, blue for total stress, the brown color for effective stress. And these are what we call stress paths. And generally, when geotechnical engineers are looking at these sorts of tests, they want to see the stress paths. The stress paths tell you rather a lot about what's going on in the test. One thing to be aware of now is that if we only see the stress path, we can't measure C' and phi' directly from the geometry because our failure line will be the purple colored line there. And in fact, the parameters we then normally quote are going to be those parameters at the top there. They are no longer C' and phi'. So when we measure the slope and intercept for that purple line, we have to convert it to C' and phi', which is just done simply from the geometry of the Moore circle by those little formulae there. So that gives us C' and phi' for that particular result. I just want to mention a couple of important points about stress paths. There they are by themselves now on that diagram. I said for a geotechnical engineer, they want to see that information. It tells you quite a lot about how this soil's behaving. And in the standard CU triaxial test, the total stress path will always be a 45-degree line because the sigma 3 is fixed. Therefore, we don't normally show it because no need. You know it's there, and you can imagine where it is, but we don't normally show the total stress path. One important thing to realize, though, and one reason to be aware of it, is that the difference between the two, of course, is the pore pressure. So you can see that in this particular case, we're generating quite a high pore pressure as we get closer and closer to failure in this particular sample. So it's really nice to know that, how the material reacts to shear. In this case, not very well. It's creating big pore pressures, not very good for stability. Also, the directions of the effective stress shear paths are related directly to Skempton's A parameter. In fact, they define it. And I've put 4 on there, 4 different directions, very simple ones. But let's see what they are. So starting over on the right-hand side, in that direction, that would be an A of 0, which what you get in very stiff, highly overconsolidated clays. The value of 1/3 is when you do an elastic solution to this whole thing. Directly upwards would be an A of 0.5, and A of 1 is 45 degrees to the left. And it's worth kind of remembering those ones, especially the 0, 0.5, and 1 directions of the stress paths. So let's put this into practice by looking at a little case study where we're going to look at some triaxial tests. These are CU triaxial tests on a recompacted residual soil. So clearly a lot of air in it when it was compacted. So they would have to use a high back pressure to achieve saturation in a material like this. But what was really interesting, you can read there the properties, I haven't got to read through that, but what was really interesting in this particular case is that they compacted the samples in 3 conditions. dry, which was on the dry side of optimum, optimum, which was at optimum, and wet, which was on the wet side of optimum. We'll see this in a minute on the compaction curve. In fact, there is the particle size distribution. You can see that this material is mostly clay with a fair amount of silt and a little bit of sand as a typical residual soil, probably a weathered granite or something like that. And this is the compaction curve. I'm sure you're familiar with these things. So it's the dry unit weight versus the water content. You can see where the optimum is there. And the three green symbols indicate the starting conditions for the three test or three sets of test specimens that were created for this particular exercise. And if I add the undrained shear strengths, when they created them, they independently measured the undrained shear strengths. So the wet one is in a soft condition, very, very soft. Optimum is very stiff, 137 kilopascals. And the dry one is kind of on the firm side. And then it's interesting that after saturation and consolidation in the CU triaxial tests, the three solid dots move to the positions on the zero air voids line given by the three open dots. So you can see that after saturation consolidation, the wet and dry samples are much the same. So here we can see the results plotted against axial strain, and you can see how the optimum specimens are giving a higher shear resistance, a higher deviator stress, and how the water pressure drops rather than stays constant compared to the other ones. Of course, there will be similar results for the other cell pressures. This is only for sigma 3 of 392 kilopascals, which is quite high, of course. But let's look at the stress paths, much more interesting. So here they are. So these are the stress paths for the three tests on the dry specimen. So what you can see there is that a fair amount of, if you can imagine those 45-degree lines for the total stress paths, you can see a fair amount of pore pressure being generated. Here is the wet case that looks similar. And you can see in each case, I've put there the best fit C dash and phi dashed values that come out of the testing. And you can, if I go back to the previous one, they're much the same. And then finally for the optimum. So I thought what's quite interesting is to put them all together. So here they are. So there we have all three test conditions put together on one diagram. And you can see the wet, the dry, and the optimum. And what's important here, and it's a very important point, is that although they're not perfectly in line, they do essentially all have the same effective stress failure envelope. And this is really important. And it makes a really important point because I sometimes see confusion with this, that although those three specimens started off their life as soft, firm, and very stiff, they do all have the same, or effectively the same effective stress strength parameters, C dash and phi dash. Sometimes people think, oh, a very soft soil, surely it must have a lower phi dashed. Of course not. The phi dash is coming from the nature of the soil grains and so forth within them. And therefore, we expect very little influence from the density on the value of phi dashed. You might see a more of an influence on C dashed, but not on phi dashed. Just to remind ourselves what the total stress line looks like, I've just left the middle group behind there. And I've posed a question here. Well, okay, they all have the same C dash and phi dash. So what's the point of high compaction? Why not just compact it badly? Well, of course, it's all about the pore pressure generated during shear. And for the red one there, the optimum specimen, you can see that the generated pore pressures are much less. And of course, that's what we prefer to have from the point of view of stability of a fill. Just one brief word about CD triaxial test. So here is switching over now. Here's a typical arrangement of some CD triaxial test results. It's actually on a residual soil from Singapore. And there are a number of tests there, different samples from different boreholes that you can see. They've all been plotted together and they are fairly consistent. This would be, again, a fairly clay, silty, sandy mixture. And the results there, just what you'd expect. But we don't normally show stress paths because they're just 45-degree lines. So all you'd get would be a mass of 45-degree lines, and it's of little interest. But one thing that we miss, if we use the CD procedure, the consolidated drain procedure, we lose that interesting information about pore pressure response to undrained shearing. And that's a shame. So that's one good reason for preferring the CU test. Also, the CU test is quicker to do, but the measurement of pore pressure has to be done really well to get a good, reliable result. So I think that's got me to the end of that discussion. And the last two things I want to do for a few minutes is to look at two questions I posed during the first webinar and see if the information we've learned about mainly today and a little bit in the last webinar is helping us to understand what's going on. And I hope it does. Now, the first question was like this. So we had a foot on a beach, and we had this thing that when you put your foot down on the beach, you tend to get it feels hard, and you get a dry patch appearing around your foot. And then, if you wait a bit, it starts to feel soft. So, can we explain that using soil mechanics? And let's see if we can. So, I've drawn a cross-section of our situation there, and I've put the water table very slightly above the surface of the sand as it was. And actually, there is a lot of what I call soil mechanics involved in this explanation. Okay, so we bring the foot down, monk, down it comes. And because we place that load incredibly quickly, then for any soil type, initially, the situation we can consider to be undrained, even for sand. So we're going to generate shear stresses to help support the weight of our foot. And because it initially behaves in an undrained way, the soil is dense and saturated, and it wants to dilate. But that's resisted initially by suction. So the effect of the suction means we have high effective stress. So the strength is high and the sand feels hard. But now there we have I've written some fairly big, large size minus U's there for the suction. But then very quickly, water starts to flow initially locally. So we get the slightly drier looking area at the top. And then as we wait a bit longer, we get further flow from further away. And essentially it all comes to equalize the pore pressures. We return to a drain condition and hydrostatic, and that's when the sand starts to feel softer again. So I hope that explanation is reasonably okay. The other one is like this, and I think this is kind of important. So I've gone slightly over my 1 hour, but I want to finish off with this one because understanding this, I think, is quite important. This was again from the first webinar, and I had these two profiles of Atterberg limits and water content from two marine clays. On the left, with the blue colors, we have the Eocene London clay, which is very old. And in the middle of that slide, we have the Holocene Juru upper marine clay. Well, actually, that's the one we saw failing underneath the embankment at the beginning of this webinar, which is a very young clay. And what I said here was, okay, let's take those two profiles, take a sample from a 2 meter depth with a 1 meter water table. They both have the same C dashed and phi dashed, but London clay is very stiff, say around about 100 kilopascals of undrained shear strength, and the Juru clay is very soft, say about 8. And can you explain this? Now, the one-word answer to this was it's all to do with stress history. But let's just see what we actually mean by that. So what I've done here, I've gone back to our Morse or our diagram of stress space. And I've got the little diagram down the bottom there of the soil sample. And I got to add some more parameters. We've got the C dash and phi dash there, and that explains how we get those green lines. And for the soft clay, I've assessed the gamma at about 16 kilonewtons per cubic meter. K naught's about 0.8. That was from the webinar number 1. And I'm assuming that AF, now AF, well, the A value varies as you shear. It's not a constant value, but for this exercise, we have to assume a single constant value, and we're going to assume 1. So we can then calculate the effective stresses on the top and side of the sample, and that allows me to calculate that Mohr circle which you see there. The red Mohr circle comes from those 2 stresses on our specimen. And therefore we can plot the stress point, which I've done with the little black X at the top, or the little black plus sign at the top. So that's the stress point defined in this stress space for the current situation in the ground. Right, there it is. The sample is there. So what do? We sample it. We take it out of the ground. We put it in a laboratory. Now, when we do that, we remove all total stress. So this total stresses all become 0, both horizontal and vertical. And assuming our AF of 1 is all right, then the stress path goes down, as you see, and it lands up on the 0 axis of shear stress. So in fact, what's happened is that the pore pressure inside our specimen becomes minus 22.2 kilopascals. It's a suction. It's the suction that's holding the sample together. Right, we then put it into our, we're going to do a UU triaxial test on it. So we put that into our test cell, and we apply cell pressure and then the deviator stress. And because we've assumed AF of 1, it goes up the path at 45 degrees until it hits the green envelope. And you can see that that is roughly an undrained shear strength of 8 kilopascals. That was for the soft clay. So, and I think that's fairly understandable. But what about the stiff clay? So let's switch over now to the stiff clay. I've assessed the unit weight at about 20. The K naught is about 3 in London clay at the top, which we saw again in webinar number 1. And I'm assuming an AF slightly negative. So what we can then do, we can now calculate the principal effective stresses inside the ground. Now, because K naught is greater than 1, it means that the horizontal stress is bigger than the vertical stress. So the horizontal stress becomes the principal major effect. Sorry, it's the major principal stress. The major one is now horizontal. Therefore, we plot the Mohr's circle underneath the line, not above it. And you'll see that the current stress point given by the little plus sign is right on the green failure line. In fact, the soil is close to what we call passive failure. The lower green line is the passive failure line. The top one is the active failure line. So that's the current state of stress in the ground. We then sample it. We take it out of the ground, and assuming our AF direction, then we end up with a stress point just near the 100 value. You can see it there. In fact, the pore pressure calculates at minus 96.6. So it's a very large suction. And the suction is the reason why this sample has such a high undrained shear strength. We then put it into our UU triaxial test with sigma 3, and then we apply the deviator stress. And it carries on that same path. I said the real one wouldn't be a straight line, but we're just assuming a constant AF. On average, it would be something like that until it hits the green line, which is taking place at around about 100 kilopascals. So that is the undrained shear strength of the London clay. And I hope that explains reasonably well what's going on between the soft clay and the stiff clay, sampled at a similar level in a similar situation and with the same effective stress strength parameters. This is not real data. I've made it up, but it's just to try and demonstrate the situation. So last couple of points to make. In fact, that calculation, or to find those undrained shear strengths, you can actually do that using this very nice formula. So we can find the undrained shear strength from C dash and phi dashed. And sometimes people see this formula and say, oh, wow, this is wonderful. We can actually calculate the undrained shear strength if we know C dash and phi dash. The only problem is you've also got to know K naught and AF, and they're difficult. And actually, I've decided to set a little problem. If anybody wants to try and do this, if anybody would like to try to derive that formula from first principles using the Morse diagram, and send us the result, the first 3 correct derivations, I will give a prize of the Mechanica Tanner book by Laurie Wesley. I'm afraid we can only offer this inside Indonesia. And the details of that are going to be given as a handout when you download the slides as a PDF file a little bit later on. It'll be available today a little bit later on. So there we are, another challenge in this particular webinar, another challenge to derive that formula. It is quite a challenge, but please have a go if you wish. And as I said, the first 3 correct derivations get a copy of Laurie Wesley's book. So that's where I've come to the end. I did go slightly over 1 hour, as I thought it probably would, but I think there are quite a few important things, and I've probably gone through that rather more quickly than I should. But hopefully you can later on study the slides in the PDF version. But just a couple of, or a few final comments. First of all, the principle of effective stress. This is an absolutely vital component of soil mechanics. And therefore it's vital to understand this for or looking at geotechnical problems. Reminding ourselves, soil strength depends on effective stress and volume change depends on the change in effective stress. As we've seen, total stress we can find out quite easily. Pore pressure in some circumstances we can find out, other circumstances are more difficult. And then effective stress can only be found by subtracting the pore pressure from the total stress. We can use either CD or CU triaxial tests to measure C dash and phi dashed. And I said my preference would always be a CU triaxial test. One, because it's quicker and therefore probably cheaper. And also because you get that interesting information about the reaction of the pore pressure to undrained shearing, which is a really important part of understanding how the soil is likely to behave in your project. When we carry out either of those test procedures, it's really important to achieve full saturation and also to make sure that the rate of shearing is slow enough to achieve pore pressure of 0 in the CD test, so very, very slow, and to make sure that we have a uniform pore pressure throughout the specimen in the CU test. Those are the references of the various things I mentioned earlier on. If you'd like to try and get some of those and you find it difficult, I'm not going to give anybody my book of the Bishop and Henkel book, but they are available. We can get hold of those things, but some of those make some really important readings. So I think that brings me to the end. Just to remind you that the next webinar will be about clay fills and looking at unsaturated soils. But thank you very much for listening. It was a slightly longer session than I thought it would be, but I will try and deal with any questions now.